And he will be, yes, and you will be talking about good manufacturing practice and chromatography. Thank you.
That's correct. Thank you. So I'm trying to share my screen here. Can everybody see the screen?
Yes.
Okay.
Yes, thank you.
Okay. So I know some speakers already talk about biomanufacturing. I'm going to link the chromatography technique to biomanufacturing. So here is a quick review of the biomanufacturing. This is our virtual biomanufacturing facility. So here, for example, we start with a cryoval, and we grow the cells in a T flask, shake flask, or spinner flask. And we scale up to the whey bioreactor. Industry go to a seed bioreactor, we don't. Then they go to a real bioreactor. And when the product is produced, they harvest, they do centrifugation or filtration. Then they still end up with a large volume of product. But the compound they're looking for, if you're looking for a protein and you harvest from 2,000 liters, actually the amount of compound you actually want is very small compared to what you end up with. So what the industry does, and we do here at Quincy College, we do a tangential flow filtration. I know Jim talked a little bit about that. So the tangential flow filtration is a technique for concentration, for concentrating the product, mostly protein. So you want to reduce the working volume. This is here an equipment from Repligen here in Massachusetts. So they use that to concentrate the protein.
Isa, can I interrupt you for just a second, please?
Yes.
Can you please put your slide on slide show? Because I believe it's
it's too small? Okay.
Yes, please. Thank you.
Okay.
Thank you so much.
Okay, good. So, okay. So I was talking about, so this is the Repligen tangential flow filtration system. So they use that to concentrate the product after harvest. So here you can see it better. So you have, after filtration or centrifugation, you end up with a product, usually without cells. And that volume is so large, and we call that feed. So you use a peristaltic pump, send the feed to a membrane. So you buy the membrane so that your protein of interest is bigger than the pore size. Therefore, your protein of interest stays in the system, in the closed system. Then it comes back to the feed. The smaller molecules, usually they are smaller protein buffer or the media gonna fall off. They're gonna fall off. So you end up with a smaller volume of product without losing your product. So that's the goal of tangential flow filtration. Even though it's called filtration, the goal is to reduce the working volume. Let's say if you do a tangential flow filtration with media, so your protein is in the media. After harvest, your protein is going to be in the media. So you don't want the protein in the media. So you want to remove the media and replace it with buffer. So that process is called diafiltration. You still use the same system, except you pump a buffer to the feed and you let the initial tangential flow filtration run. So then you end up with, by replacing the media with a buffer. Or you can also replace one buffer with another. That's also called diafiltration. So if anybody has a question, please ask as we go. So that I may still have the slide and we can discuss about it. So now we go to chromatography with a smaller volume of harvest. we do diafiltration. So the protein is in a buffer. You can store the buffer or you can do chromatography right away. So the chromatography was developed by a Russian botanist called Mikhail Tsvet. So in English, it's going to be Michael, but in Russian, it's Mikhail Tsvet. So he's the one who developed the technique. At the time, he didn't have modern equipment, so he used calcium carbonate as a column, and he used ether as a mobile phase to run those compounds from plants. So what he did, he ground plant leaves, and he was able to run them and separate them based on the color. So at that time, there was no detector. So the only way you could know that you are separating is by seeing it visually. So he used compound different colors. Therefore, you could see them in the column because they exhibit different colors. Today, they are detectors, even powerful detectors. And we know, like somebody else said before, most of the compounds we separate today don't have colors. So, but because of the detector, we can actually see them. See a graphical representation called peaks. So the chromatography, I will define chromatography as a separation technique that involves three main components. So there is what is called the stationary phase, which is a column. The column is actually the one that makes the separation, because the column is a tube that has a resin in there, material beads, and those beads react with the molecules, the sample you put in. The second part of the chromatography is the mobile phase. The mobile phase is what's the tool you use to push your sample through the column. That can be liquid, it can be gas, or it can be supercritical fluid. I'm going to talk later about that. So this is, for example, liquid that are used in chromatography. These are examples. You can use buffers, or you can use organic solvent to run in biomanufacturing. Usually it's liquids that are used. You can use also gas as a mobile phase. That's used in gas chromatography. So these are different types of gases that are used. You use a gas tank that is under pressure. So when you open it, the gas comes out, and the gas pushes the sample through the column. So this is a gas chromatography column. It's like a coil. It can sometimes be as long as 100 meters. Then actually there are molecules. There are molecules inside our column that will react to the sample. So there is what is called an injector. So you inject the sample, and the gas called carrier gas pushes the sample through the column. Because of the pressure, it pushes through the column, and the sample reacts with those molecules. And if they are different, they come out at different time in the detector. So the detector actually going to pick the material, and today there are computers, so you're going to use the data and exhibit the data in the form of graphical representation called peaks. So because the molecule come at different time, you see different peaks. That's if there is a good separation. There is also another mobile phase is called the supercritical fluid. So that comes from what we know in chemistry or in physics, all the compound, for example, they have a certain state depending on the pressure and the temperature at which they are. If you take water, for example, At room temperature, water is liquid. If you put it in the freezer, it becomes solid, ice. If you put water, you boil water, it becomes gas. So that is true for most, if not all, the compound. If you play with the temperature and the pressure, you can change them from one state to another. So that's done with, for example, carbon dioxide. Carbon dioxide, they use carbon dioxide gas and they play with the temperature and pressure and get to a point where it's not totally solid and it's not totally gas and it's not totally liquid. And that point is called a supercritical point. And when you get to the substance at that point, for example, carbon dioxide is used in its supercritical fluid form as a mobile phase. And the rest is the same as a gas chromatography. You just push your sample through the column using that as a mobile phase. In that case, the type of the chromatography is called supercritical fluid chromatography. This is here an example, just an example of how caffeine can be separated very well with a supercritical fluid and from coffee. Detector, this is the third part of chromatography. So you have a mobile phase, stationary phase, and you have detectors. This is a detector from instrument like HPLC, very powerful detector. That the way it works, you use ordinary light or UV light, and that light is sent through a flow detector, using lenses to guide the light and the filter to guide the light through a flow detector. The flow detector is where you put your sample. Then the light is gonna cross the sample. So then the sample is gonna react, depending on what molecule are in the sample, react. And whatever comes out goes to a grating, which is another part of the detector. The grating is gonna split the light into different colors. Those colors correspond to different wavelengths. So correspond to different wavelengths. Then the grater are gonna send it to a diode array detector, gonna collect those wavelengths and send them to a software. They're gonna process them and show peaks. So, and that's a graphical representation, and you can see that on a screen. And if there are different molecules, and they come out at different time, you see different peaks. So, in a summary, that's how I summarize chromatography. So it has 3 different groups depending on the mobile phase. So if the mobile phase is a liquid, the chromatography type is called liquid chromatography. If the mobile phase is a gas, it's called gas chromatography. If the mobile phase is a supercritical fluid, it's called supercritical fluid chromatography. Now, in biomanufacturing, what is used the most is a liquid chromatography. Gas and supercritical are used also, but in QC, quality control. But in manufacturing, the liquid chromatography is used most often. If you take the liquid chromatography itself, it's divided into 2 groups. There is one group that uses columns and another group doesn't use columns. It's like a paper chromatography or thin layer chromatography. Those are called non-column or planar chromatography. Then you have the chromatography that needs columns. And within that chromatography group, depending on the type of column you use, you can also define again the type of liquid chromatography it is. If you use a resin that is size exclusion resin, it's called a liquid size exclusion liquid chromatography, for example, same as ion exchange or affinity. So this is a resin. So this is the material that is present in a column. In manufacturing, these are familiar. So the resin is sold in this form in containers label packed together. But what happens is those resin are made by companies, and you may or you may not know exactly which molecules are within that resin. So if you take one resin, which is a bead, if you look at it under the microscope, if you actually touch the resin, it feels like a sand, so small beads. If you look at under the microscope, they look like this. But what industry does, this is called the backbone of the resin. They use this backbone. It can be silica, it can be synthetic material. These are beads, and they attach molecule to the surface of the beads. Once they attach molecule, different molecules gonna give different properties. So then they get a resin with different properties, depend on the surface modification of the beads. So that's when you can actually buy affinity resin because of the surface, or you can buy your size exclusion resin because of the molecules on the surface of the beads. But when you buy, especially in industry, they have to pack their own columns because the column is so big, you can't really buy it pre-packed because the resin can fall apart or can crack during the transportation. So they pack the columns on site. Here at Quincy College, students learn how to pack a column, so they prepare what is called a slurry. The slurry is the homogeneous solution of the resin plus a packing solution. It can be a saline solution or it can be buffer. So you take the buffer, you measure the resin, you mix the two until you get homogeneous solution. That's when you transfer it into the column, into the tube. So that's called a slurry. So in industry and company that make columns, it's very important to know how to prepare the slurry by making some calculation. So if you want a column with a certain height, you have to know how much resin you have to prepare to get that height, because you have to compress the resin also. So this is, for example, you buy a resin, most of the time it comes in a storage solution. So the easiest way to do that, you can shake it. You shake the resin with the packing solution. You transfer it into a graduated cylinder. If you bring the total volume, the mixture volume to 100 ml, and you let it sit overnight, when you come in the morning, you're gonna see the resin gonna settle. You're gonna see two layers. Then you're gonna determine the concentration of resin, how much resin was in the 100 slurry. So that's how you know how the resin is concentrated. And whatever the packing solution is, you can remove it and replace it with the solution you want and make another slurry, and you can actually pack your column. So once you know the concentration of your resin, these are calculations you can do. These are I'm just showing you, but most people don't do this. They don't have to know how to calculate this. You can just use the software to do it. But once you know the concentration of the resin, the manufacturer of the resin is gonna tell you what the packing factor is, or what is the compression factor is. The CF is a compression factor, and the PF is the packing factor. Compression factor is, you get that from the manufacturer. Then you use that to calculate how much resin you need and to get a certain height of resin. So this is just an example how they do that. So once you have your right slurry, the right amount of slurry, and you put it in the tube, if you compress it too much, you get something like on the right. So the beads are too tight. If you don't prepare the right slurry, if it's not homogeneous before you transfer it into the column, into the tube, you get beads that are in the column, but they are not evenly distributed in the tube. So there is space, bigger space and smaller space between the beads. And that will not pass the column packing test. So if you don't pass the column packing test, you can't use your column, especially for GMP application. The column that looks right,
Interesting.
Yes. So the column that looks right is the one in the middle. It's not too tight, but it's not also, it's even, the beads are evenly distributed. If the disadvantage of the overpack one, the one on the right, is that you may crack the molecules that are on the surface of the resin. So you change the property of the resin if the molecules are not there. The other thing is you may use too much resin that you don't really need to, and the resin is expensive. So if you get it right, that's the ideal solution. If you get it wrong, you have to unpack it and repack if it's GMP, because you can't use it. Now,
So
yes.
do you mind me asking so how do you know when you've packed it correctly? How do you measure that?
You do a test. Yeah, that's the next slide.
Okay, sorry.
So this is the next slide. These are two tests that are often used. One, the simpler one is the one on the right called asymmetry test. So after you pack your column, you attach it to the instrument. You can use acetone, but most places are going to use sodium chloride because it's easy to wash out and it doesn't really stay on the column. So you use sodium chloride and you run a sample of sodium chloride and you collect a peak with a conductivity detector. The UV detector will not see it. You collect a peak like this. So you look at the highest point of the peak, that's called the apex. And you draw a line that's perpendicular to the x-axis. So you split the peak into two. Then you can measure the base, or usually most companies are gonna measure at 10% of the height of the peak. So the 10% of the height of the peak, you measure the first wave, because now the peak is split into two. The first wave is called A, the second part is called B. So then you do the ratio B divided by A. If it's a perfect, it's gonna be 1. But usually you don't get perfect, but you can get a range that is acceptable. The company will tell you the range, but usually it's between 0.8 and 1.2. So if that ratio is there, then your column is well packed. If you don't pass that, you have to do it again. So then there is another test which involves more calculations. It's called the HETP. So that has to do with the height of the plates, the number of plate and the height of the plate. So those are theoretical plates. They are not real plates. If you have more plates, it means the column gonna do a better separation than if you have a less plate. So another example is if your column is packed well, the N is the number of plate. You're gonna get a higher N than if the column is not well packed. You're gonna get a lower N with the same amount of resin. So these are the two tests you do. Even a Repligen here, they have a department that packs only columns, and they sell the columns. So these are the two tests they do.
So these are the tests now that people are doing when they sell their columns.
Correct, yes. If you pack the column on site, you have to do this test before you can use it.
Mm-hmm.
So liquid, the instrument that is often used today's very powerful instrument is the AKTA system. It's a liquid chromatography. It can be, there are two versions. There is the 25 and 150. So the 150 is just bigger, but they all use the same software. These machines now are produced by GE, Citiva. GE is split into two now. There is a division called Citiva. So these are called, the AKTA Pures are called protein purification machines. The reason is they do chromatography, regular chromatography. They use mobile phase, they have a detector, they use a column. The only reason is the detector is a single wavelength, sometimes dual. It doesn't scan. So you can see only some molecule, 280, which is typical to protein. So that's why it's called protein purification machine. And a lot of companies use this, and there is a lot of employment in this area because a lot of companies buy them and they don't have people to run them. The other thing is they build them for GMP application because these machines are pumps, but the pumps use alcohol as a lubricant. They don't use oil. So if you have a GMP facility, make it easier because alcohol is already permitted in a GMP environment. So you don't have to do other justification. So this is part of the software at the bottom. The software, you can actually control the instrument with the software. So you can see the different parts. The green is the mobile phase moving along all the way to a fraction collector. And you can see if you click on the column, you can change. This one, you can actually attach up to 5 columns, but you can't run the 5. You can run 1, but you can prepare 5 and you can attach them when you're ready. You just switch them using the software because they have different positions. So this is a fraction collector for the AKTA. So the AKTA can actually, when it sees the peaks, you can use the software to collect the peaks in a fraction collector. So you can tell it, I want to put every peak in a tube, or I want to put a certain volume of mobile phase into a valve. So then when the software is going to show you which peak is in which valve, because the valves have numbers. And on the software, on the screen, you're going to see the numbers corresponding to where the peak is. If the peak is too big, it can be in 2 or 3 valves, unless you tell the instrument not to use the volume. So you can also program it so that you collect only peaks. In that case, if the peak is too big, you're going to overflow. It won't switch to the next unless a second peak comes. But if you collect based on peak and volume, so when you put a certain volume of the peak in one valve, if the valve is about full, you're going to switch to the next valve and put the same peak. So if the peak is big, you can see that the peak falls in 2 or 3 valves, and you can collect those valves and test them for your product. So these are tests that are usually used. The most common students use, for example, is the SDS page. So you collect your peaks in different valves, Now the molecules are separated. You have different vials, different peaks, but you need only one molecule, one compound that of interest. So you can test each vial where you have peaks. Then you can find which vial has your right compound. So then that's what you use. And another test is ELISA test. Sometimes ELISA is more accurate, and it's fast, except it's not available for all type of proteins. So you can, there are other tests you can do, the MS, the LCMS, or the GCMS to identify your product of interest. Now, the columns. The columns, depending on these are, depending on the material in the column, the type of material. So if the material is made to separate your molecule based on their size, so the column, you're gonna call the column size exclusion column. And the chromatography gonna also be called size exclusion chromatography. If you're using mobile phase for the size exclusion column, if you're using buffer, that's called aqueous solution. So if you use buffer, it's gonna be called gel filtration. If you use organic solvent like alcohol, it's called gel permeation chromatography. So that's for the size exclusion resin, a size exclusion column. Now there is also ion exchange column. If your resin is charged to bind negative or positive proteins, then you're gonna call it ion exchange chromatography. So you can buy a resin that is negatively charged to bind compounds that are positively charged. Or what industry does, because the resin is expensive, you can buy one type, and you can actually change the charge of your protein, because the protein usually don't have one charge because they have different amino acids, and the amino acids have various charges. So in a protein, you're not like a DNA where the whole thing is negative. Protein have mixed charges. So the way to get around with that is you actually find what is called the pI of the protein. The pI is the pH at which the protein is neutral. So it's not a charge. The total charge is 0. So if you know the pI of that protein, you can prepare a buffer that has a pH above the pI or below the pI, so that you can actually use that buffer to change the charge of the protein, make the protein totally positive or totally negative. Or then you can run like SDS page, just similar. So then you can use this type of resin to bind your molecule. There is also another type of material called the hydrophobic interaction resin. It's, if you use hydrophobic interaction resin, it's gonna be called hydrophobic interaction chromatography because you're using hydrophobic interaction column. So that has to do with the hydrophobic regions of the proteins. So the proteins have hydrophilic and hydrophobic regions. So what you do is you use that resin to bind that resin has affinity with the hydrophobic region of the protein. So if the protein has larger region of hydrophobic amino acid, then it's gonna bind tightly to the column, and opposed to the one that has a less hydrophobic region. Then if you use a salt, usually ammonium sulfate is used a lot in industry because it doesn't really damage most protein. It's good for most protein. So they use that a lot. You can use ammonium sulfate, and you can gradually change the concentration using what's a gradient mobile phase. Then you can actually elute the molecule based on the hydrophobicity. So the ones that have larger region, hydrophobic region will not elute at the same time as the one that have a smaller hydrophobic region. So you can elute them and they come out of the column at different times. So you separate them that way. And you can collect them in a fraction collector. You can do the test also and find out where your right protein is.
You know, that's the problem with green fluorescent protein is it's hydrophobic chromatography.
Yes.
And students have a harder time with that when it's the first thing they've ever purified, trying to explain hydrochromatography to them.
Yeah, it's very confusing to explain. Yes, that's totally true. What I do, I explain like oil and water. Oil and water. If you take a glass of water and you let it sit flat, you let the glass sit on a table, and you use a pipette to put a drop at a different spot of oil, the drop of oil is gonna stay separate. But if you close that glass and you mix it, you shake it, and you let it sit, you're gonna see that the drop of oil gonna go together, and also the water gonna stay together. So then, so that's how I try to explain. So it can be very confusing.
Yeah, Ying Su just said, yeah, we do his tag too, because that's like a one-step purification, but then that's something different.
Yeah, each tag is, well, they usually put that in affinity chromatography.
Right, exactly.
Yeah.
But then you have to be able to cleave off the His.
Correct, yes.
The other thing about the BioRad hydrophobic interaction HIC column is it's a methyl column, and so the resolution isn't the best.
Mm-hmm.
Uh-huh.
So if it was a phenyl column or if it was a C8, you'd get better resolution. But anyway, it's not the best.
Yep.
That's true. So now, that's where usually the E-stack is a part of this affinity. Affinity works more like antibody antigen. If you are the best resin, you can actually use antibodies to separate, except it's very expensive. So that's why they use the metal affinity resin. So which is you buy the resin, it's not ready to bind yet, but you have to charge the resin. So what you do, you pack the column and you use a metal that has affinity with our resin. It can be copper, it can be a nickel, it can be zinc, depending on the resin. And you can actually dissolve that metal and you run it through the column until it's saturated. Then you wash away whatever didn't bind. Then the column becomes charged. So when it's charged, it can bind certain protein that are affinity with metal. So, and you can, the impurities can be washed away when you wash the column. And then you can use another solution to elute the compound. So the other thing we talk about when we talk about chromatography is equilibration of the column. So sometimes that can be, it's not clear to students. So equilibration is when you pack the column, when packing the column, you shouldn't let the column dry. If you can pack the column with one buffer, and you may need to use another buffer to run your column, to push your sample through the column. So because the resin is in the first buffer, you have to wash that buffer out. So you wash it out until it's gone completely. Then you can start your process. So you wash your column with alcohol, and you wanna wash. You store your column in alcohol, and you wanna wash away that alcohol. You have to use either water or buffer to wash out, and make sure the system is filled with the new solvent you want to use. So that's called equilibration. Usually you can monitor that if you have a UV detector or pH detector or conductivity detector. And when they become flat, you know that your system is ready, and then you can inject. So the wash has to do with just like a regular washing. If I store my column in alcohol, and because I don't want bacteria to grow in it, because I'm going to use it next week. When I come next week, I want to use it. I want to wash away the alcohol. I can use water, run water through it, remove the alcohol. Then I can use a buffer and to replace that water that was in the line until I fill the system up with the buffer I want to use. So that's, you remove everything that you don't want. That's a wash. Wash the buffer. The other thing is, yes.
Could I ask a question? We just do a real low tech, just load the column. The students load the column themselves. They're passing over proteins across. We're using an anion exchange, DEAE, and it's stored in a tris buffer, but we use it in a phosphate buffer, and our bead volume shrinks by half. Why is that happening? Can you tell me?
It is shrinking. So it may be because the column was not well compressed. So there is a space between the adapter and the resin. That's what he's saying. Do you see space between the adapter and the resin? How do you know it shrinks? Because you see space in the column.
They load the column, and the buffer that it's stored in is dripping down. When it stops dripping, it has a certain height, and then when they equilibrate it with a different buffer, the height shrinks.
The height of the resin?
Yeah.
Is that, so do you see space between the adapter and the resin?
No. It's like the beads shrink.
Huh. Oh, yeah. The other thing you want to know is maybe check is the solution you use, are they compatible with the resin? If they are not compatible, yes.
I think it's a dehydration effect. Water is drawn out.
Yeah, Carol, it's in ethanol, right? Your storage?
It's stored in a tris buffer, 25 millimolar tris.
No ethanol?
Mm-mm. That's how the beads say to be rehydrated.
I know to store, usually buffer is not a good storage solution.
Okay.
So you want probably, the beads may be damaged. So if they are cracked or the molecules are removed from the surface of the beads, it's gonna be smaller. The height is gonna go down. That's also possible.
Yes, I just want to say that is most likely because when I used to work in the industry, if the pack column reduces by a certain percentage, we would have to inspect the beads to make sure they're not broken, because then they will not do your separation accurately.
Yeah, that's correct. Yeah, if the surface, the molecules that are mounted on the surface, if they are cracked, then the height is going to decrease.
And they're going to crack just from using a different buffer?
Possible if the buffer is not compatible with that.
All right, thank you.
If there is a microbial growth, because the column is stored in buffer. Usually it's stored in alkali or alcohol. But the manufacturer is going to tell you exactly which solution is good to store the resin.
Yeah, our staff will make the beads. They rehydrate the beads that week, so it's not a microbe problem.
Oh, okay. Okay,
so it's probably an incompatible buffer.
Yeah, that's possible. If it doesn't stay too long, if you don't leave it for many days in the buffer, microbial will not be a problem.
Yeah.
So the next step will be column regeneration. So if you use the column, usually we all use the column many times. So if you use the column many times, sometimes what happens is the compound, the samples or the protein, they get stuck. Some of the protein, there is a buildup on the surface of the resin. They don't get washed out completely. And that can actually change the property of the column. You may not even bind well. So you can throw the resin away, use a new resin, or what we usually do, most of us, is we regenerate the resin, make it look like new. So usually what happened, the manufacturer gonna tell you which solvent you can put your resin in, so it's gonna actually dissolve the impurities and it won't damage the resin. So you can use that, and you can dissolve the protein that are built up on the surface, and then you can wash everything out, and the column may look better. Or you can pass again the HTTP test. So you do that and do the test again until, if it passes the test, you can continue to use it. If it doesn't pass the test, then you can use it, especially if it's a GMP, because it has failed the HTTP or the asymmetry test. Okay, so I think that's the end.
So we have a break coming up at 2:15 Central, which is about 7-8 minutes from now.
Yes.
So if anybody has questions, please go ahead and ask Isso. And then at 2:15, we have about a 15-minute break.
Yes.
Following that, Dr. Dennis would be giving us an overview of the COVID-19. So we'll open the floor for questions for another, I guess, 7 minutes. Thank you.
I have a question.
Yes.
How would you go about screening for which method would be best to use, or which methods would be best to use?
For a protein?
For a protein, for instance, yeah, if it was just like some product recombinant.
You mean which resin to use?
I guess which purification method or resin? In the workflow, it says there's multiple polishing.
Yeah, there are so many of them. The answer, usually, if it's in the research lab, then you don't even know, if nobody has worked on that type of protein, you don't really know where to start with. So you start with the resin that is cheaper, and you try to see which resin is going to separate better. Usually the size exclusion is easy. You use one type of solvent. You can use that to see if it actually can separate. Even if it doesn't separate, will that get rid of some impurities, at least reduce the number of molecules you want to separate from each other. So size exclusion may be the first thing to do, especially if you know the size of your protein. So then you're gonna see that once you eliminate some impurities, then you can use another type of resin. For example, ion exchange, if you know the pI of your protein and you don't have too many molecules, you can use ion exchange and use the technique that is to change the pI of your protein. You use the pI to prepare a buffer that's going to charge your protein a certain way. And that also can help you separate your protein from many other impurities. Most of the time, you're not going to get the final answer until you use at least 2 or 3 resin before you get a pure product.
I think it's a useful example to ask the students that give them a protein, give them the characteristics, and have them develop a purification scheme and tell them to use 3 to 5 columns. And there are sort of basic guidelines that you want to use your least expensive resin first. At the same time, you want to use your most exclusive resin first. Now, you have some tension there because usually affinity chromatography is your best resin, but it's usually your most expensive resin. So have the students do that. And in industry, they rarely use gel filtration because the resolution isn't good enough. They did in the early days, but what I typically do is have them say don't use that one because you wouldn't use it. On the other hand, if you have them think about the philosophy behind purification, what you're trying to do is use a variety of protein characteristics to isolate your protein. So if you're looking at a protein with the same charge and then you elute it, well, any protein that is going to co-purify with it has the same charge. But then if you use hydrophobic interaction chromatography, then a co-purifying protein has the same charge and the same hydrophobicity. And then if you do size, then a protein to co-purify would have to have the same size, the same charge, the same hydrophobicity. And at some point, if you put enough of those together, then it's impossible and your protein is going to be pure. But that's an example I would, or that's a challenge I would give to your students.
Yes. So the other thing is many companies that sell a resin, they give you small columns of a variety of resins. Sometimes they have free samples. So that you can use that as just give them an exercise with those columns, so they'll come up with a better answer.
You know, the pandemic has been helpful in this regard because you get to do a lot more thinking before you get in the lab. And giving them 4 different proteins. I know I was talking to one of our faculty members, Kasau, 4 different proteins, 4 different PIs, all different types of chemical, physical properties. And then I said, you have bulk purification first, and then maybe polishing with 1 more, and say you only get 2 columns.
Yes.
And it's got to be cost and ease. And stability of protein too, because I remember when I had to purify a protein, ornithine decarboxylase, it lost 50% of its activity within 24 hours once I broke it open out of the cell.
Yes. Yeah, that's why they require work in a cold room in industry, all of that. So even if you use a column, the column has a chamber where you can actually circulate cold water to maintain the sample cold inside the column.
Yeah. But see, then I was really mean. I only gave them 2 columns to do, Jim. 1 for bulk, 1 for fine tuning. Go for it. Figure it out.
Yes. Yeah, that's good.
Yeah, and if you don't have a cold room, you can always use what they call those deli cabinets or beer coolers.
Oh, yeah.
And set your columns up there, and it's very, very cost effective.
Yeah, and I have to admit, I liked it better than having to wear my down jacket all the time. Yep. That got old.
You know, as a non-academic, man, you guys are spilling all the secrets and all the conspiracies that I thought, making it hard on the students. Now I know. All right.
Yeah. Well, you know, it really makes them better protein chemists. Yes. When you make them you force them to think about chemical and physical properties of what they're trying to purify, and the fact that they can change, you know, purification by changing up the pH of the buffer, which is something they don't always think about.
Yes, it's true.
because they don't think about the PI.
I
Yeah.
loved the challenges. The harder the science, the more intriguing. I didn't necessarily do well, but it was fascinating.
Yeah, I was telling the group, in chat that when I did affinity chromatography on ornithine decarboxylase, I used pyridoxal phosphate because that was one of the groups it bound to.
Yes.
It died 50% in 24 hours. I only had 2 column choices. And I discovered hydrophobic chromatography accidentally because I used the first linker I used was 8 carbons long to put the pyridoxal phosphate on it.
Yes.
And I had to make my columns, remember when we had to make columns?
Yes.
And I found that it was binding better to the linker than it was to the pyridoxal phosphate. And I said, wow, what's this called? And someone said to me, oh, you just discovered hydrophobic chromatography. Oh.
Yeah, that's a good one.
There's a question in the chat on how you take the laboratory long skinny chromatography columns and turn them into one of those big commercial 2-meter chromatography columns. And it's a pretty interesting bit of engineering where and usually comes from the bottom up, that the material comes in and then it flares out and then it goes in a regular level, or in a regular layer up through the column. And so the difference between a long skinny column and one of those flat flying saucer types commercial columns is in the engineering of the flow of the material through.
So if we don't have any other questions, let's take a break and get back at 2:30 Central, 3:30 Eastern for our next session. Thank you so much.
Yes, some of those columns, Jim, are two meters across and 2 meters tall. And they weigh a whole lot, which means you really need to think about floor loading when you have an entire room filled with those things.
Yeah. Good to see you, Dennis. Really good to see you. Yeah.
Yeah, I don't know if anybody else is staying on or whatever, but my first dive into we did hydrophobic chromatography for GFP in Mindy's lab. And then I repeated it in Orgo lab. I did some twist and tried to merge the two or whatever. So I was already well on my way into fermentation. I didn't know it. Was to load, what were they, like 50? No, had to be almost, there were 100-liter columns. So I'm dumping it. My first taste with ion exchange resin of any, like real resin of any kind, and was packing a 3 ion exchange beds over and over and over. Luckily, I didn't have to do we have like 500-liter ones or whatever, so really big ones. I operated them, but I didn't get to load them. But this is cool stuff. I like this. It was a good presentation, by the way.
Hey, Joey, I wanted